clay minerals also, 1:1, 2:1, 2:2. So for today's class, I have given you classification of silicate minerals. So in that itself, you can open that link and see that one. Types and classification of silicates. So we know that silicates are made up of silicon, oxygen, aluminium. So based on the arrangement of that tetrahedral structure and octahedral structures, silicates are classified into around 7 groups. See, single tetrahedron, if it is linked with another tetrahedron, two tetrahedrons in a chain form, it is called as chain silicates. If it is, again, the arrangement, if there are many layers of these silicates, they are referred to as double chain silicates. Sheet silicates, one above the other. So in the pictures, you can see this. You have open that link also. You can see this where I'm sharing. So see, we have orthosilicates or neosilicates. Then we have pyrosilicates. It is also called as sorosilicates. Then we have cyclic silicates or ring structured silicates. Cyclic means ring structured silicates. We have chain silicates, that is pyroxenes, example. Then we have double chain silicate, example amphibole, sheet silicate or phyllosilicate. Then if the tetrahedron is arranged in a three-dimensional structure, it is called as Tacto Silicates. So you should remember all these. Usually they would ask for subjective type of questions. What are the types and classification of silicates? That time you have to write these 7 types of silicates. See what, so coming to each one of them, orthosilicate. So, or it is called as neosilicate or island silicate. In this orthosilicate, it is single, the simplest silicate, which contains silicate SiO4 4 minus tetrahedral units. So the basic structural unit of orthosilicate is indicated in the diagram in what I have drawn in the notes also. I have shown you the triangle shape wherein one silicon atom is surrounded by 4 oxygen atoms. So this is referred to as orthosilicate. The orthosilicate ion is a strong conjugate base of a weak orthosilic acid. Silicic acid is SiHSiO4. You know sulfuric formula, H2SO4. Like that, silicic acid is HSiO4 is silicic acid. So here the orthosilicate minerals are rare and it is usually found with cations which form highly insoluble salts. So examples of orthosilicates given here are phenosite, also it is called as phenocryate, when the formula is Be2SiO4. One more example is Vindimite, that is zinc silicate. This is a minor silicate ore of zinc, which is green in color when observed under UV spectroscopy. Here you see the valency of these ions. Be beryllium 2 plus, zinc 2 plus ions are tetrahedrali surrounded by the oxygen atoms of the silicate. Another example of this orthosilicate is olivine. You have seen in your fundamentals of soil science course. Olivine, the green colored mineral. This has orthosilicate structure, that is a single tetrahedral structure, and it is green in color. Here the cations present are octahedrali coordinated in the oxygen atoms of the silicate. So see the cations present in olivine are Fe2 plus, Mg2 plus, and they are the two cations present. Another example is zircon. zircon silicate, the oldest mineral which is found on the earth. So the coordination number of zircon 4 plus is 8. What do you mean by coordination number? See, I told you that every uh, atom or compound to be stable, it should have octet rule. So here Zr 4 plus. To become octet, it requires 4 plus ions. So to become 8. So the coordination number is the amount of electrons present or the valency required to become octet. Then your next group of classification is pyrosilicates. Pyrosilicates, also called as sorosilicate or disilicate. Here, two tetrahedrons are joined together by one oxygen atom. See, the linkage is one oxygen atom joining two tetrahedrons. Here, this contains Si2O7, 6 minus ions, which are formed by joining two tetrahedral structures which share one oxygen atom at one corner. That is, one oxygen is removed while joining. Structure, this is called as pyrosilicate or sorosilicate. So this is less basic in nature compared to orthosilicate. Means here, yeah, there we have magnesium, that is why it is basic orthosilicate. Here we do not have magnesium or anything. Here we have orthosilicate. Here we have one mineral nature containing pyrosilicate. Example, tortivite, which has formula is Se2Si2O7. This is pyrosilicate, is two tetrahedrons joined together. So you should remember, one is single tetrahedron is orthosilicate, two tetrahedrons joined together is pyrosilicate. Next, coming to many tetrahedron joining together, that is cyclic silicates. Cyclic silicates contain the formula SiO3 taken n times 2 to the power of n ions, which are found by linking 3 or more tetrahedral silicate units, star-shaped, cyclically. Each unit shares 2 oxygen atoms with other units. These are called as cyclic silicates. See the diagram? So it gives you a star-shaped. There are many tetrahedral joining ring form or cyclic form. So they are called as cyclosilicates. Example is benitoite. Formula is BeTiSiO3 taken thrice, containing 3 tetrahedron arranged cyclically. Beryl silicate containing 6 silicate rings. You see 1, 2, 3, 4, 5, 6. It is a star-shaped tetrahedral structure. It is an aluminosilicate. Each aluminum is surrounded by 6 oxygen atoms. Therefore, it forms octahedral structure. So, it is well-known varieties of beryl include emerald and aquamarine. These are the minerals, green colored minerals. So this is cyclic silicates. The fourth one is chain silicates. Example, pyroxene. You might have seen the mineral in the fundamental course. So chain silicates or pyroxenes, they are linked. Each tetrahedron joins another tetrahedron structures. See here, ions which are formed by linking n number of tetrahedral units linearly. Each unit shares 2 oxygen atoms with other units. So example of these chain silicates are spodumene. Formula is lithium aluminum silicate, a pyroxene mineral consisting of LiAl SiO3 taken twice, then diopside, which has basic cations like calcium, magnesium, silicate, then wolstonite, which has calcium silicate, Ca3SiO3 taken thrice. So these are chain silicates, which are linearly arranged here. The tetrahedral structures are arranged linearly and linked together by oxygen atoms. The formula of these cyclic silicates as well as chain silicates is SiO3 taken N to N minus. Therefore, these are considered as oligomers of the unknown silicate ion. So first one ortho, 1, 2 double chain is. Second one, it is sorosilicates. Third, cyclic silicates. Fourth is chain silicates, that is pyroxenes. So next, coming to the double chain silicates. So double chain silicate example is amphibole. Here the general formula of double chain silicates or amphiboles is Si4O11 taken N6 N minus. Here there are two types of tetrahedron. They are sharing three vertices and those sharing only two vertices. So you can see the two star-shaped diagrams wherein they join with each other or double layer. See the first layer, with the first layer, the linear, first you should draw the linear chain structure. Second layer is another linear chain structure. When these two layers, one above the other, join together, they form double chain structure. And when they form this double chain structure, they form the star-shaped or the octahedral unit structure. So they are called as double chain silicates. Previous one is single chain, linearly arranged tetrahedral. Here two linear layers are joined together, forming the double chain silicate structure. Example is asbestos. So these are non-combustible fibrous silicates. They have been used for thermal insulation material or sometimes brake linings, construction material, filters. You might have observed these asbestos filters in your even water units, these osmosis units. You're in the home, you have different aquaguard everywhere. So asbestos has a double chain silicate structure, which is having the ability to filter the dust or waste materials. These are carcinogenic amphiboles affecting the lungs, asbestos. Hence, the applications are restricted nowadays. Then tremolite is another example. Formula is calcium magnesium silicate. Here the single and double chain silicates are collectively known as inosilicates. So what are inosilicates? Inosilicates is a combination of single and double chain silicates. You should remember this, inosilicates. Next, coming to sheet silicates or phyllosilicates. Phyllo means leaf, layer wise arrangements. So you can see single chain, double chain, the another layer, triple chain. So it forms a sheet. One above the other, all tetrahedral structures are arranged means it forms sheet or layer wise horizontal silicate structures. Here the general formula of sheet or phyllo or two-dimensional silicate structure is Si2O5 taken n times to the power of 2n. So each silicate tetrahedron here shares three oxygen atoms with others and therefore forms two-dimensional sheets. So these silicates are said to be cleaved with similar to that of a graphite. Here the layers are held together by weak van der Waal forces. Example are for phyllosilicates talc, mica. Mica you have seen mica layer wise. So the structure of mica is like this, and it is the main ingredient of soapstone. It is the softest material with a smooth and greasy touch. Mica is another example. We have muscovite mica, biotite mica, lepidolite. Then we have clay. Clay is also a phyllosilicate. It is an aluminosilicate with sheet structure. Example, kyanite. Kyanite is aluminum silicate. AlSiO5 OH 5 times. So that is the sheet silicate. Next, coming to the three-dimensional silicates or tectosilicates. It is referred to as tectosilicates. So what is a tectosilicate? The general formula of these three-dimensional tecto or framework silicates is referred to as tectosilicates. Here, the oxygen atoms of silicates are shared with other tetrahedra, forming a three-dimensional network. So, example, quartz is an example. Then we have cristobalite. Then we have feldspar. We have zeolite. Example of tectosilicates. You should remember the definition and an example and the drawings of these types of silicates. So overall, a few points about silicates are, to sum up, silicate minerals are very common in the earth crust because oxygen and silicon are the most abundant elements present on the earth's surface. The degree of polymerization denoted by oxygen to silicon ratio is like this. Greater the degree of polymerization, lower will be the O-silicon ratio. The values for orthosilicates is 4:1, while for tectosilicates it is 2:1. Here means sharing of the oxygen with one silicate ion. So with increase in the degree of polymerization, there is decrease in the charge per silicon atom as well as the basicity of the silicate mineral. Therefore, silicon dioxide is an acidic oxide. Basic silicate minerals usually react with weak acids, therefore undergoes weathering. Uh, so these structures you need to draw. I will be giving you assignments after few classes which will help you to write your exam. For midterm exam, I am going to include all these structures, the type of minerals, the classification of minerals. You should know how to draw these structures. You should practice these structures. This is clear now. See, some of the examples, questions also are here. You just go through those questions also. And once again, you can see that video also. There also it is explained well. See, have you seen that videos? You see the videos here. Same thing.
Hello students, welcome. I am Aditya from adicchemistry.com. In this presentation, I am going to explain the types and structure of silicates along with examples.
See, again, it's a repetition so that it will be easy for you to listen.
So what are you waiting for? Let us jump into the presentation. So first of all, what are silicates? These are the minerals containing silicon and oxygen in tetrahedral SiO4 4- units, which are linked together in several patterns. You can see the SiO4 4- unit on the right side. The silicon atom is surrounded by 4 oxygen atoms tetrahedrally. This is also called orthosilicate or simply the silicate ion. Now let us have a closer look at the silicate tetrahedral unit. It is actually the side view, but in most of the silicate structures, the tetrahedral unit is shown in top view. The blue circles are representing oxygen atoms, while the thick red dot represents the silicon atom. Now the types of silicates. Depending on the linking pattern of silicate tetrahedral units, the silicate minerals are divided into first one orthosilicates, or you can call nesosilicates. Second one is pyroxene or sorosilicates. Third one cyclic silicates or ring silicates. Fourth one chain silicates or pyroxenes. Fifth one double chain silicates are also called as amphiboles. The sixth one is sheet or phyllosilicates. The seventh one, the three-dimensional or Tacto Silicates. Now let us deal with them one by one. The first one is Orthosilicates. These are the simplest silicates containing discrete SiO4 4- tetrahedral units. You have seen them already. I am showing both side view and top view here. The examples are phenacite, willemite, olivine and zircon. Next one is pyrosilicates, which are made up of Si2O7 6- ions. These are formed by joining two tetrahedral SiO4 4- units, and they share one oxygen atom at one corner. So this is the oxygen atom shared in between two tetrahedral units. This is the side view actually, and this is top view. At the center you can clearly see the oxygen atom which is shared in between the two tetrahedral units. The example is Totevitite. This is the silicate mineral of scandium. Next one is cyclic silicates, which contain SiO3 taken n times with 2 n- charge. There are 3 or more tetrahedral SiO4 4- units linked cyclically. So here 3 tetrahedral units are linked cyclically. Here there are 6 silicate tetrahedral units linked cyclically, and there are 6 oxygen atoms shared in between 2 tetrahedral units. And the examples are benitoite and beryl. Now the chain silicates, which contain again SiO3 taken n times 2 n- ions. Here n number of tetrahedral units linked linearly, not cyclically, it is now linearly. You can clearly see the pattern. So the tetrahedral units are linked linearly here. Here the examples are spodumene, diopside and wollastonite. The next one is double chain silicates. Here the general formula is Si4O11 taken n times with 6 n- charge. There are two types of tetrahedra here, those sharing 3 vertices and those sharing only 2 vertices. And the examples are asbestos and tremolite. Next one, sheet silicates. Here the general formula is Si2O5 taken n times with 2n minus charge. So this is a structural pattern of sheet silicates. You can see a beautiful structure here. And the examples are talcum, micos with general formula X2Y4 minus 6 Z8 O20 OH and F 4 times, where X is potassium, sodium or calcium, Y is aluminium, magnesium or iron, Z is silicon or aluminium, and the examples are muscovite mica and lepidolite. And the clay is also a sheet silicate. It is an aluminous silicate actually. Kyalinite is another example. Finally, the three-dimensional silicates or Tacto Silicates. The general formula is SiO2 taken n times. All the oxygen atoms of SiO4 units are shared with other tetrahedra, and thus by forming three-dimensional network, all the oxygens of tetrahedra are shared. Examples are simply silica. This is you can call them quartz, tridimite or cristobalite. There are three forms, crystalline forms: feldspar, geolites, ult, etc. These are actually three-dimensional aluminosilicates with the SiO4 4 minus units replaced by AlO4 5 minus units. Now few practice questions. SiO3 taken n times with the 2n minus charge may be the empirical formula of option A cyclic silicates, option B pyrosilicates, option C chain silicates, option D both A and C. You know the answer. Both cyclic as well as chain silicates have the same formula. The general formula for them is SiO3 taken n times 2n minus. Next question. Amphibole silicate minerals consists of A. Single silicon tetrahedra, B. Chains of silicon tetrahedra, C. Double chains of silica tetrahedra, option D. Sheets of silica tetrahedra. You know double chains of silica tetrahedra is the answer, because amphibole silicates are otherwise known as double chain silicates. Next one. In normal silicates, each silicon atom is surrounded by 5 oxygen atoms in a trigonal bipyramidal geometry, 4 oxygen atoms in a square planar geometry, 4 oxygen atoms in tetrahedral geometry,
Yes,
6 oxygen atoms in octahedral geometry.
you
You know the
can hear
answer
now.
is option C.
Yes, ma'am.
Just because this is
Another
tough,
question. Which
you
of the
need,
following
that's why so many
silicates
times
is
repetition.
referred to as
You need to
pyroxenes?
practice writing this.
Single chain silicates, phyllosilicate, tectosilicates, double chain silicates. And you know single chain silicates are called pyroxenes. So option A is correct. Now one more last question. B8Ti Si3O9 is a class of orthosilicate, cyclic silicate, chain silicate, sheet silicate. And we know this is a cyclic silicate. Already we have seen this. So option B is correct. Okay, that is all for now. For more information and practice questions,
So
visit the following page.
this is clear now. So you know the types of silicates, the classification based on the arrangement of the structures, tetrahedral unit and the octahedral unit. So you need to practice this. So for an assignment also, you need to write these, draw all these structures, 7 type of, for next class. Next, when do I have class? Today is the
Tuesday,
third,
ma'am.
yeah. By for Tuesday, you people just draw all these structures and upload it to me. I think you people will come back by that time. Anyway, you write in white sheets. When you come, you can submit, because this will be asked for your exam. I will ask for midterm exam also. In the final exam also, this question will usually occur. So it's better you practice these structures. The single tetrahedral, double single chain, double chain, then more than 3 octet. You need to practice these structures. Even I've given another PDF also, I think I have sent now. So you write the assignment of,
Okay, ma'am.
is it clear so far?
Yes, ma'am.
Hello,
Yes, ma'am.
clear or no? I can't hear you.
Clear, ma'am. Hello, ma'am.
Yeah, it's audible, right?
Yes, ma'am. Audible, ma'am.
So for whatever I've explained, you need to write and submit to me, okay?
Okay,
About
ma'am.
these structures. So from the first class, it's clear for you. Soil colloids, properties. For the exam also, I'm going to ask you all this. Nature and properties of soil colloids, those 10 properties. That is electric charge, surface area, absorption, whatever is in the syllabus. According to syllabus, I am going, no, so I've completed first what is soil chemistry, scope of soil chemistry, then the components, organic, inorganic components of soil, which forms the soil colloids. What is soil colloid? Difference between colloid, crystalloid. What is a missile? What is a unit cell? Then adsorption, sorption. Then the type of 1, 2:2 type. These are then today's classes based on arrangement of the tetrahedron, octahedron. So far, we have completed the clay structures. You have to know the diagram of kaolinite, the montmorillonite, vermiculite, brucite. 4 drawings also are important. So the difference also you should know, what is the difference between brucite and vermiculite. So in the last class, I explained to you that brucite means magnesium will replace aluminum ion. If magnesium is present in the place of aluminum, That mineral is called as brucite. What is brucite also? You should remember. So these questions I'm going to ask, I'm telling now only for your exams, so that you will at least read. I'm just telling you. Then these structures are very important. You should know. And why do you think all these structures are important in the soil? See, because of these clay mineral structures only, the cations will get absorbed on this clay complex. So when we apply any fertilizers, any manures to soil, so these edges of the clay surface area only will absorb the nutrients. And when the plants are required, it will give it to the roots, or exchange will take. Next class is ion exchange mechanisms. So how these nutrients will get exchanged to the root hairs. See, all cations are absorbed on this clay complex. Cations means plus charge. If it has to be absorbed by the roots, if the roots are having positive ions, it will not take up the nutrients. It should have the opposite charge. So root hairs usually will carry a negative charge. So how do you think these root hairs will carry negative charge? You just go through and tell me in the next class. If I tell now, you will. So curiosity should be there. You should just see how root hairs will give out anions, minus charge. Only if the root hairs are minus charge, these nutrients will be taken up by the plants. So you have, that is why this chemistry of soil colloids is important for nutrient ion exchange mechanisms, for uptake of nutrients by the plants for growth and development. Clear now why we are studying these structures? What is the need for knowing these bonds, how it is held together? See, oxygen is there, so hydrogen bond will form, then van der Waals forces will be involved. So all these bonds are also important to keep the structure of the clay in an ideal shape or ideal condition for the nutrients to get absorbed. So once the nutrients get absorbed on these clay complexes, again the pH of the soil will change. Suppose say more iron and aluminum get absorbed on the clay complex, such soils will become acidic. In case calcium, magnesium will be more, that cases soils will become saline. If sodium ions get absorbed on these clay edges, it will become alkaline. So again, for reclamation also, we need to know what type of cations are present on this clay complex. So the structures of the clay is important for all these studies, and even for pollution control measures also. Sometimes heavy metals also will get absorbed in these clay complexes. Again, these clay edges have different positions, E, P. So in some of the drawings you would have observed small letters E, P. E means edges, P means the position where it is absorbed. So when you draw only, you can understand that structure of the clay. So how do you think they have studied all these structures? Again, it is through electron microscope and through X-ray diffraction studies. So electron microscope, because it is not viewed under the normal microscope because of the smallest size of the particle. And sometimes it is rod shaped, layers shaped also. X-ray diffraction means, see, when X-rays are allowed to fall on these clay particles, the rays will get distracted. Means it may get reflected, it comes back. So based on the distance of that X-ray diffracted, uh, we can know the type of ions present on the clay complex. For example, say iron is present on the clay, then aluminum, then potassium, calcium, magnesium. So when these rays, X-rays are made to fall on the clay complex, if potassium is there, it will have a particular distance of ray reflecting or distracting. It may be more. Then, so each calcium also may have a shorter length. So magnesium may have a shorter length. So based on the distance of distraction of the X-ray light, we can know the presence of different ions on these edges of the clays. So based on that only we can know that on the clay, for example, mica, vermiculite mica, what type of ions are present, whether potassium is present, magnesium is present. Suppose a brucite mineral, then magnesium will be present, means so what type of ray is being distracted. So the distance gives you the presence of these ions. So like this, they have been studying this clay structures. Okay, that so much is clear now. Okay, fine then. If it is for today's class, this much is enough. So we will wait and see if you are going to have offline class next week. When you have to draw and submit all these to me. Fine.
Okay, ma'am.
So when you come back, practical class also we may start. How is the COVID in your places? All normal. Everybody is fine.
Yes, ma'am.
Then I think they will invite you. I think today itself, Sunday, some people are coming. I think first years are joining tomorrow.
Yes, ma'am. 31st first years are coming.
So you people are not yet informed.
No, ma'am. Still no notice came.
Okay, fine. So the class is clear now. Some more thing I will send, and I've sent one more PDF to you. Just go through that. Okay.
Okay, ma'am.
Okay, fine then. I will end the class. You have
Okay,
taken the attendance?
Yes, ma'am.
Screenshot.
Yes, ma'am.
Okay, fine then.
Thank
You
you,
send
ma'am.
it to me. I will end the meeting. Yes.
Okay. Okay. Thank you.
Okay, bye.